Okay, we are back again from the same page, right. So, now next we will discuss that your what you call that damping one, right. So, now damping torque component due to delta psi f d we call k d delta psi f d minus 0.3255 j delta delta, that means this term, this second term it is j delta delta. Look here, only understanding is required, nothing else, only so this term if we make k d due to delta psi f d, this is the meaning, is equal to minus 0.3255 j delta delta, right. So, this is negative, actually this is negative, right. So, that is what we are writing here, that k d delta psi f d is equal to minus 0.3255 j delta delta, this is equation 292. If you look throughout this, just if you see this dynamics and control, that equation we have come up to 292, right. So, nowhere you will find such a long number of equations, but just to maintain the continuity and for easy understanding. So, easily you can refer to which equations are. So, if I break all these things, then things will become complicated and this equation comes to 92. So, when I teach here in the class, I mean for our own student, right. So, at that time actually when I make this 292 or 300 equations, so they feel that this continuity is maintained and nothing actually is wrong, everything is fine, because I had to collect all this information from various places, right. So, that is why this continuity has been maintained, otherwise in a particular topic you will not see that so many equations, that 292 equations, further it will increase, right. So, it has been made such that continuity will never be lost and all the equations are mentioned, immediately will go back and you can verify, right. So, next we will come to the meaning of this one, that it is actually 90 degree out of phase because j delta delta, right. So, if you look into this, that go back to that, if you go back to that block diagram, that figure 30 or a previous figure does not matter, that delta, now you will know why it is called in phase. Now, if you look into this, delta delta is equal to omega 0 s omega 0 by s into delta omega. They go to figure 30 and just see this, you go to figure 30 and just see this, right. Now, we can write delta omega r is equal to s delta delta by omega 0, right, and s is equal to j omega. Here you are substituting that s is equal to j omega, here you are substituting. If you put s is equal to j omega, then how it looks like, delta omega will be j omega delta delta upon omega 0, right. So, that means j delta delta, that means just hold on, that means j delta delta, right, this j delta delta is nothing but is function of delta omega r and d by omega 0 upon omega, right. So, your what you call that means k d delta psi f d actually it is equal to minus 0.3255, then actually k d, just we have seen delta psi f d I am overwriting is equal to your, we got minus 0.3255 j delta delta, right. Now, if you replace j delta delta by this term delta omega r omega 0 upon omega, then this is replaced by j delta delta omega 0 upon omega into delta omega r. At that time you can see it is function of delta omega r, right. That is why we call it is in phase with delta omega, right. And if it is, if you put in terms of j delta delta like this one, j delta delta like this one, right, at that time we call 90 degree out of phase, right. This is the your what you call the meaning. So, if you do so, it is actually coming like this, omega 0 upon omega, because j delta delta has been replaced by omega 0 upon omega into delta omega r. This is equation 294. Now, when omega is equal to 10 radian per second, we have taken earlier also, that is 1.6 hertz, frequency is 1.6 hertz, and you put omega is equal to 10 radian per second, right. Then and this omega 0 we have taken a 60 hertz system. So, omega 0 it is actually we say 2 pi into 60, because we have taken that nominal frequency f 0 is equal to 60 hertz, and rotor frequency oscillation we have taken omega is equal to 10 radian per second, that means approximately it is 1.6 hertz, right. So, if in that case Kd delta psi FD will be minus 0.3255 into 2 pi into 60 upon 10 delta omega r, this is equation 295, right. So, if you simplify, it is become Kd delta psi FD is equal to minus 12.27 per unit torque divided by per unit speed change, right. So, in the absence of any other source of damping, the total Kd will be Kd delta psi FD, because just let me go up that in that if data is available or no, here it is next page, your what previous page, that we have to consider that Kd is equal to 0 for this analysis, right. That is why your just hold on, let me go back here. So, in this case what happened, that for our analysis, that in the absence of any other source of damping, because for this thing we have taken no initial data, Kd is equal to 0.0, we did not consider any damping, rather capital D, Kd is equal to 0.0, we have not considered any damping thing. So, in that is why in the absence of any other source of damping, the total Kd will be Kd due to delta psi FD, right. Now, let us make some analysis. Now, when K is equal to 0, delta psi FD is entirely due to armature reaction. This we have seen earlier. The effect of the AVR is to decrease Kd for all positive values of K, right. So, any positive value of K is that it decreases actually Kd, the damping coefficient. So, that net damping is minimum most negative for K is equal to, say, the net damping is minimum, that is most negative for K is equal to 200 and is 0 for K is equal to infinity, right. So, this one you please do it as an exercise, take K tends to infinity, right. So, for low values of K, the effect of the AVR is to decrease K very slightly. Let me move up little bit. So, the effect of your AVR is to decrease K very slightly, right. The net case being minimum at K is about 46. This is an exercise for you, right. If K, this you find out, K is equal to 46, if it is, then K is being minimum at K of about 46, because the function is given in terms of K, you please find out, this is an exercise for you. So, as K is increased beyond this value, K increases steadily, right. Or graphically also you can plot and you can see this. In MATLAB you can easily plot, right. For infinite value of K, the torque due to delta psi FD is in phase with delta and hence has no damping component, right. So, for infinite value of K means when K tends to infinity, you will find torque due to your delta psi FD is in phase with delta and hence has no damping component. That means that delta T component due to delta psi FD, that means delta, just hold on, that means delta T due to delta psi FD will be function of only delta. So, I can put it is function of delta, but no J delta term will come, right, due to your what you call for infinite value of K, that means when K tends to infinity, right. This is a small exercise for you, you please try this one, right. This is small exercise for you. So, if I try to make everything, then it will take more time. So, now, we are normally interested in the performances of excitation system with moderate or high responses, right. For such excitation system, we can make the following general observations regarding the effect of the AVR, right. So, now number 1, this you will keep it in your mind, with K phi positive, the effect of the AVR is to introduce a negative synchronizing torque and a positive damping torque component, right. When K phi is positive. So, what we have done is that we have taken negative value minus 0.12. you try with plus 0.12 and see this whatever has been mentioned here whether it is matching or not. So, with k pi positive, the effect of AVR is to introduce a negative synchronizing torque, just opposite it will happen, and a positive damping torque component, just opposite. We saw that your some constant into delta delta minus some constant j delta delta, but if you take positive value it will be minus into minus some coefficient your constant delta delta plus your some positive your some constant your j delta delta, just this you do it for k phi is equal to plus 0.212, right. Now, number 2, the constant k phi is positive for low values of your external system reactance and low generator outputs, right. Now, the reduction the reduction in case due to AVR action in such cases is usually of no particular concern, because K1 is so high that the net case is significantly greater. Actually, delta TE is equal to your K2 delta psi FD plus your K1 delta delta. So, although due to this that your your delta T component due to your delta psi FD will be very less actually compared to your K1 value. So, it has not that significant, because ultimately it will be K1 plus your Ks delta psi FD into delta delta, right. But Ks delta psi FD if it is reduced does not matter, because K1 is quite high for a your what you call given operating condition, right. Now, when with K phi negative, right, the AVR action introduces a positive synchronizing torque that we have seen for k phi is equal to minus 0.12 and a negative damping torque component that also we have seen just now, right. And this effect is more pronounced as the exciter response increases, but details cannot be done in this video course or even in the regular classroom course, because it involves a actually huge computation and it takes time, right. So, next this is one. Next we will what we call next we will consider that power system stabilizer. So, method this simplification other thing will come later. So, whatever block diagram we have seen, look whatever block diagram we have seen, all these things were okay, all these things were okay, we have already derived this all this thing, right. In addition to that, we are adding one power system stabilizer. Basically, it is a lead lag stabilizer form, and input to the stabilizer is delta omega r, that is the speed deviation. Of course, different versions of stabilizers input signal to the stabilizer is available, but our interest is only for the classroom purpose. So, this is actually power system stabilizer function. Basically, it actually what we want actually it adds your what you call that we want to damp out the rotor frequency oscillation. For this an additional signal is taken, and that way we use that your power system stabilizer, basically lead lag stabilizer. Detailed analysis for lead lag stabilizer for this course in the class, it is really difficult, but when somebody does simulation or some your research work or thesis work, at that time one can consider this for the simulation purpose, right. But this is actually PSS means that is your power system stabilizer. So, now if we put power system stabilizer thing, then what will happen, that if you look into that this signal is coming here, this signal is coming here, this output of the stabilizer signal is delta Vs, which is here, right, and this is delta V reference, this is my exciter, and rest of the block diagram remains same, right, rest of the block diagram will remain same. So, in this case block diagram will be coming back to that, but only thing is that this delta Vs thing whatever you see here, these are additional signal is coming here, additional signal is coming here, right. This rest of the things are okay. Therefore, what will be our your observation or what will be our study, we see this due to this power system stabilizer, what is its effects on the damping, right, by rotor frequency of oscillation, right. So, that is why this diagram I have made it before. After that your what you call, after that all this your what you call all this analysis regarding stabilizer, whenever needed we will come back to this figure. This is actually figure 31, right, this is figure 31, right. So, now the basic function of power system stabilizer is to add damping to the generator rotor oscillation, right, by controlling its excitation using auxiliary stabilizing signal, right. So, that is why feedback is given here, right. So, excitation using auxiliary stabilizing signals. Now, that is delta Vs. Now, to provide damping, the stabilizer must produce a component of electrical torque in phase with the rotor speed deviation. This we have to see it, right. Purpose of a PSS is to introduce a damping torque component. A logical signal to use for controlling generator excitation is the speed deviation, that is delta omega r. So, this input to this stabilizer this thing we have taken delta omega r, right. Now, if the exciter transfer function GXS and the generator transfer function between delta EFD and delta T are pure gains, that means in between this thing, and this thing, I mean in between this thing, right. If it is a, just let me go back, if it is a pure gain, right, that is your a direct feedback of delta omega would result in a damping torque component. So, that we have to see how we can make the direct gain, right. However, in practice both the generator and the exciter, that is depending on its type, because different type of exciters are there, right, exhibit frequency dependent gain and phase characteristics. Therefore, the PSS, that is power system stabilizer transfer function, that is we call GPSS function of S, should have appropriate phase compensation, that is why we call phase lead lag compensator we use. Details we cannot analyze on this course, but I will explain those, right, to compensate for the phase lag between the exciter input and the electrical torque, right. So, in the ideal case with the phase characteristics of GPSS, that is stabilizer transfer function, being an exact inverse of the exciter and generator phase characteristic to be compensated, right. It will be a pure gain, it has to be made it, right. The PSS would result in a pure damping torque at all oscillating frequency. That means that lead lag network or lead lag compensator you have to design in such a fashion such that if that lead compensator, it will compensate the lag one. We will take a small example and we will try to explain that one how things are, right. For example, suppose this is just for the sake of understanding. For example, suppose we have taken k is equal to 200, right. Now, as I told you, since TR is very small in comparison to T3, previously we have taken one example, I told you at that time that T3 is equal to your what you call that 1.91 second we took, or where TR is 0.02 second. So, TR can be neglected. So, previous example we have considered TR and we have analyzed. I suggest that previous example you put TR is equal to 0 and repeat the same analysis for your Ks delta psi FD and Kd delta psi FD also as an exercise. So, your from the block diagram, that is your, this is from the block diagram, whenever I have missed this one, this is actually figure 31, right. With TR neglected, the delta psi FD due to PSS is given by, right. So, what you will do, you will go back to this figure, same as before, you find out that delta T due to delta psi FD is equal to K2 into delta psi FD, right. So, this only additional thing is delta Vs term is coming with this thing, and TR is neglected, then this will be simply 1, this should not be there. So, in that case, and this value is we have taken, this one is K, simple gain, then what will happen, this delta Vs will come plus delta V reference minus your from here it is coming minus K5 delta and here it is coming your what you call minus K, your plus here it is minus, here it is plus. So, it will be minus K, that is delta V reference plus delta Vs, then minus K5 delta then minus K6 delta psi FD into K, right. Then bracket will be your what you call, the bracket will be closed, right. Then with that minus K4 delta will come, right, into K3 upon 1 plus ST3, and here another K2 will be multiplied. That is your delta TE due to delta psi FD, because from your undergraduate your what you call that transfer function model. So, this one you will find out. So, again and again I am telling that delta T has two component, one is K1 delta delta, another one is that is K2 delta psi FD, that is another component due to delta psi FD, but this K2 you have to multiply, right. So, that means, so when we write like this, that it will be delta psi FD, I told you delta V reference plus delta Vs minus delta V1, here I did not substitute that, I will substitute into K minus K4 delta delta, again into K3 upon 1 plus ST3, right, is equal to delta psi FD, right. So, delta psi FD is equal to, then little bit simplification if we make K V delta V reference plus delta Vs minus delta V1 into this term K3 upon 1 plus ST3 minus your K3 K4 upon 1 plus ST3 delta delta is equal to delta psi FD, right. So, just hold on. So, that means that delta V1 is equal to K6 delta psi FD plus K5 delta delta from that block diagram only. So, here you substitute, I mean from that block diagram, that is your figure that previous figure, that delta V1 is equal to this one, and your TR is neglected, TR you have neglected, right. So, directly you substitute that your delta V1 is equal to this one, and then minus K3 K4 upon 1 plus S3 delta delta, right. So, now let us assume delta V reference is equal to 0, right, you assume delta V reference is equal to 0. So, if delta V reference is equal to 0, then this equation can be written as delta psi FD is equal to K3 K upon 1 plus ST3 in bracket delta Vs minus K6 into delta psi FD minus K3 K5 K upon 1 plus ST3 delta delta, then minus K3 K4 upon 1 plus ST3 delta delta. Just one thing I would like to mention, that so many terms and huge mathematics is involved. By chance you hope everything is correct, I think everything is correct, but if you see by chance any term is missed or anything, just please let me know, then I can rectify this, right. But I believe things are okay, right. So, this one if you make delta V reference 0 and just simplify, that this will be like this, right. Now, therefore, delta psi FD we can rewrite this K3 K upon 1 plus ST3 minus this term we are rewriting, minus K6 delta psi FD plus delta Vs, then these two term we are writing together. So, minus in bracket K3 K5 Ka plus K3 K4 upon 1 plus ST3 delta delta, right. So, that means upon simplification, bring this thing to the left hand side, bring this delta psi FD term to this left hand side, then it is actually delta psi FD plus K3 K K6 upon 1 plus T3 delta psi FD is equal to K3 K upon 1 plus ST3 delta Vs, right, minus K3 K5 K plus K3 K4 upon 1 plus ST3 delta delta, right. So, this side you simplify left hand side. So, it is becoming actually 1 plus ST3 plus K3 K K6 upon 1 plus ST3 delta psi FD is equal to K3 K upon 1 plus ST3 delta Vs minus K3 K5 K plus K3 K4 upon 1 plus ST3 delta delta, right. So, further simplification will give you that your 1 plus ST3 plus K3 K K6 delta psi FD is equal to K3 K Vs minus K3 K5 K plus K3 K4 delta delta, or this term can be written as that delta psi FD can be written as that your K3 Ka upon 1 plus ST3 plus K3 K6 K delta Vs minus K3 into K5 K plus K4 upon 1 plus ST3 K3 K K6 delta delta, right. So, now when that means this term has come to this equation because of this power system stabilizer delta Vs, right. And earlier if it is not there, previously this term was there, right. But in that case your what you call, you have to neglect TR, you just neglect TR and do not consider delta Vs, then you will see this term is there. But due to delta Vs, right, due to delta Vs, this term has been introduced, right. So, that means we have to see that is providing actually damping. So, that is why this term due to and this is the output signal from the stabilizer is delta Vs, right. So, that means what we will do, just try to understand this, right. It is only understanding, mathematics is you can easily make it, right. That means, whenever we are writing this, that delta psi f d upon delta Vs. So, if you write delta psi f d upon delta Vs, right. So, this term will be there and this term is delta delta upon delta Vs, both side you divide by delta Vs. So, delta f d upon delta this term plus minus this term into delta delta by your delta Vs. That means, due to stabilizer this term has been introduced, right. This term has been introduced. That means this term, only this term we are writing, this is delta psi f d it due to your PSS, this much you write. This is I have not written here, because while I am teaching in the classroom I am telling them that this is the thing, but your case delta f d this is due to PSS, only this term we will consider now, right. This term we will not consider, we will only consider due to delta PS, only this term, first term we will consider, right. So, we know, so we know that all the parameters initially given and K is equal to 200 we have taken and T3 also we have taken, so I think 1.91 second, right, and K3 also 1.333 and all other parameters previously we have taken some parameters, you substitute all these parameters, right. You substitute all these parameters, then you will find that every time let me tell you, this is actually due to PSS, right. This is actually due to PSS. So, there will be no confusion at all, right. So, you put all these parameters and this delta f d delta Vs, it is actually due to power system stabilizer, this term has been introduced, right. So, because we have two components that we know K2 delta psi f d, that is one component due to that, but this term is coming because of PSS, right. So, if you put this one and simplify, it will become 66.66 divided by 21 plus 1.91 s, right. So, this is coming actually, and if you try to simplify you will find some lagging angle will be coming, right, when you put s is equal to j omega. Now, we will examine the PSS phase compensation required to produce damping torque at a rotor oscillation frequency we have taken earlier 10 radian per second, that is 1.6 Hz, right. So, with s is equal to j omega, you put j omega, your omega is equal to 10, right. Therefore, it will become delta f d upon delta Vs will become actually 66.66 upon 21 plus j 19.1, right. Now, numerator and denominator, now numerator this is equal to 66.66, numerator and denominator you multiply by j your 21 minus j 19.1 divided by, if you multiply it is 21 square plus 90.1 square, right, because j is a complex operator. So, just multiply numerator and denominator by 21 minus j 19.1 and you simplify, right. So, if you simplify, that is delta t, now we are changing the term delta t delta t ps, right, that is delta t due to PSS rather, right, will be K2 into delta psi f d due to PSS, that I wrote earlier also that term, right. So, therefore, at a frequency of 10 radian per second delta t PSS upon delta Vs, now we can write like this, right, is equal to, now meaning is clear to you, meaning is completely clear to you, it will be K2 66.66 upon 21 plus J 19.1. Now, if you simplify this, right, and multiply by this K2, so K2 is 1.5, it will be 1.5 into 66.66 upon 21 plus J 19.1, and this one I told you simplify, multiply numerator and denominator by 21 minus J 19.1, that I have just told you, right. If you do so, it will come 3.522 angle minus 42.3 degree. This lagging angle is coming, right, and we have to set the your what you call gain is a pure gain, that means you need a lead compensator just to your what you call just to nullify this gain, this angle minus 40 angle 42.3 degree. Thank you very much, we will be back again.